Right now, somewhere on the Ethereum blockchain, there is this mathematical equation fighting a high-speed war against an artificial intelligence.
Yeah, and they're fighting over fractions of a penny.
Right, exactly. Fractions of a penny, and there are no humans involved at all. There's, no sleep breaks. It's just pure cold code locked in this invisible, endless combat.
It's completely invisible to the average person, yeah. But, I mean, that specific combat is what literally holds the modern decentralized economy together.
Wow.
If that invisible war stops, the markets just freeze entirely.
That is wild. Well, welcome to the deep dive. Today we are looking at the architectural blueprints for a machine. Specifically, we've got a source document that outlines step-by-step how to build an on-chain market-making algorithm for crypto pairs.
A very specific set of pairs, too.
Right. Yeah. The blueprint focuses on USD Plus paired with wETH and USD Plus paired with cbbtc.
Before we go, a single step further, we should probably establish a baseline on those assets. Because the architecture we're discussing today, it's highly dependent on the nature of what is actually being traded.
Yeah, let's do it. So USD Plus is a yield-bearing stablecoin, right? It's pegged to the US dollar, but it actually generates native yield.
Mm-hmm.
And then you have wETH and cbbtc, which, I think most of you listening have heard of Ethereum and Bitcoin, but the W and the TB prefixes always trip people up.
No, constantly, yeah.
So break those down for me.
Well, it comes down to the fundamental language of blockchains. You cannot directly trade native Bitcoin on the Ethereum blockchain.
Right, because they're totally different networks.
Exactly. They operate on completely different underlying architectures.
Right.
So to bring that massive Bitcoin liquidity into the Ethereum decentralized finance ecosystem, which, we call DeFi, you have to wrap it.
Okay, so you essentially lock up a real Bitcoin in a vault somewhere, and a smart contract issues you a token that represents that locked Bitcoin on the Ethereum network.
Correct, yeah. So cbbtc is just Coinbase wrapped Bitcoin. It's an ERC20 token, which is the standard token format on Ethereum, backed by Bitcoin, held by Coinbase.
Got it.
And wETH operates on a really similar principle. Native Ether is actually not an ERC20 token itself.
Really?
Yeah, because it was built before that standard even existed. So to easily trade Ether against other ERC20 tokens and smart contracts, you have to wrap it into wETH.
Oh, that makes sense. Okay, so we have our standardized tokens, we have our stablecoin USD Plus paired against our volatile assets, wrapped Ethereum and wrapped Bitcoin.
Right.
Our mission today is to understand how you take complex traditional financial math, inject it with a reinforcement learning AI known as PPO.
Which is fascinating on its own.
Oh, absolutely. And then drop it into the incredibly chaotic environment of the blockchain to synthesize, quote unquote, optimal market liquidity.
And all without a human ever touching a keyboard once it's turned on.
Exactly. So, okay, let's unpack this. Because to appreciate the sheer magnitude of what this algorithm is doing, I feel like we have to travel back in time a bit, right?
Yeah, we have to understand the problem it was originally built to solve. We have to look at the vendor's dilemma.
Right. The source material gives us a highly tangible analogy to start with. So imagine a traditional physical market. You are a vendor. You've set up a little stall selling apples.
A completely timeless economic scenario.
Right. As this vendor, you are always ready to buy an apple slightly below the going market price. And you are always ready to sell an apple slightly above the market price. You aren't growing them.
Yeah.
You aren't eating them. You are literally just standing in the middle.
And in traditional finance, down on Wall Street, this is called being a market maker. You are providing the service of immediate liquidity.
Which people pay for.
Exactly. When a trader wants to buy Apple stock, or in our case, wETH, they do not want to sit around for 3 hours waiting for another human being to naturally decide they want to sell at that exact microsecond.
Right. They want it now.
They want to click a button and see the asset in their account instantly.
So the market maker absorbs the friction of time. They take the other side of the trade immediately. And they get paid for doing this through the spread, right?
The spread is the lifeblood of liquidity. It is simply the gap between your bid price, which is what you're willing to buy for, and your ask price, what you're willing to sell for.
So if the market price for an apple is $1, and I quote a bid of 99 cents and an ask of $1.01, that 2-cent gap is my profit margin.
Yep.
If someone sells to me, I pay 99 cents. If someone buys from me, I get $1.01. I just captured those 2 pennies.
And if you do that thousands of times an hour, Those pennies turn into millions of dollars. I mean, for decades, human market makers stood on trading floors doing exactly this.
Screaming at each other.
Right, and then computers took over, building these massive order books that quoted bids and asks in milliseconds.
I mean, I'm listening to this, and it honestly sounds like a money printer. You just stand in the middle, capture the spread, and rake in cash.
It does sound nice, doesn't it?
It sounds too nice. Wait, I know financial history well enough to know there are no free lunches. What is the catch here? What if the market just completely crashes?
And there it is. You've just identified the most dangerous existential threat to a market maker. It's called inventory risk.
Inventory risk.
Yes. This is the entire reason the complex mathematics in our blueprint even exist.
Let's visualize that risk for the listener. Let's say a catastrophic news report comes out claiming that apples cause some terrible disease.
Okay.
The market price of apples plummets from $1 down to 10 cents in a matter of minutes.
Total panic.
Right. What happens to my stall?
Well, if you are a naive market maker, your algorithm is programmed to always buy slightly below the current market price. As the price drops to 90 cents, everyone in the market runs to your stall to sell their apples.
Because I'm the only one buying.
Exactly. You buy them, thinking you can flip them for 91 cents, but the price immediately drops to 80 cents.
So nobody buys from my ask, but everyone just keeps dumping apples onto my bid.
You are catching a falling knife. The price goes to 70, 60, 50 cents. Your algorithm dutifully keeps buying because it thinks it's capturing a spread.
Oh, man.
By the time the price hits 10 cents, your cash reserves are completely drained, and you are sitting on a massive, rotting mountain of apples that are virtually worthless.
I am left holding the bag. I've bought all the way down the death spiral.
This has actually happened in the real world. During various flash crashes in traditional equities, and especially in crypto, poorly designed market-making algorithms have literally bankrupted firms in seconds.
Just because they couldn't shut off their buy orders fast enough.
Exactly. They couldn't stop buying during a unidirectional market crash.
So the opposite must be true as well, right? What if someone discovers apples cure aging? The price rockets to $10.
The math is equally punishing, just in a completely different direction. Your algorithm places sell orders at $1.01. The market violently buys all your apples. You are completely sold out in the first millisecond of the rally.
So I'm sitting on this tiny pile of cash while the asset I used to own just skyrockets to $10 without me.
You suffer a massive opportunity cost. In either scenario, the crash or the moonshot, the vendor's dilemma is that a static strategy guarantees you will either accumulate way too much inventory of a dying asset or completely sell out of an exploding asset.
So we need a dynamic defense mechanism. We need a way for the algorithm to realize, hey, I have way too many apples. I need to fundamentally change how I price things to save my own life.
Which introduces the absolute centerpiece of our blueprint, the Avellaneda-Stoikov model, often referred to simply as the AS model.
The source text leans really heavily into this, and I want to spend significant time deconstructing it. Because this isn't just theory, right?
No, not at all.
This is the foundational mathematics of high-frequency trading.
Developed by Marco Avellaneda and Sasha Stoikov back in 2008. It completely revolutionized how quantitative firms thought about managing inventory risk on electronic order books.
Okay, we're going to break this formula down. The goal of the AS model is to constantly calculate two very specific things: your reservation price and your optimal spread.
Right.
Let's start by looking at the baseline metrics the formula takes in as fuel. The first variable is the current market price, denoted in the math as S sub t.
The S stands for spot price, and the T is the current time. This is the global consensus price of the asset at this exact millisecond. If we are trading USD plus against wETH, it is the exact exchange rate right now.
But the spot price doesn't tell you how dangerous the market is. For that, we need the second variable, which is volatility, represented by the Greek letter sigma.
Yeah, volatility is really the heartbeat of the algorithm. Mathematically, it is usually calculated as the standard deviation of asset returns over a specific rolling window.
In plain English, how violently is the price whipping back and forth?
Yes. A low sigma means the market is a calm pond. The price is drifting lazily. A high sigma means you are in a hurricane.
The price is spiking and crashing violently.
Exactly. The AS model constantly reads sigma to understand the environmental risk it is currently standing in.
Now, we hit a variable that I find genuinely confusing in the context of crypto. The text defines capital T as the terminal time, or the time horizon.
Right.
But In traditional Wall Street finance, I know terminal time is usually the ringing of the closing bell at 4:00 p.m.
Yes, traditional market makers absolutely refuse to hold a heavy, unbalanced inventory overnight.
because when the market is closed, things happen.
Exactly. Geopolitical events can happen, companies can release disastrous earnings reports, and the market maker can't react. When the opening bell rings the next morning, the price might gap down, and their inventory is suddenly toxic.
So as the 4:00 p.m. closing bell approaches, as terminal time approaches, the traditional algorithm gets increasingly frantic to balance its books back to a completely neutral state, converting everything to cash before the buzzer.
Exactly. But you spotted the structural conflict. Ethereum never sleeps.
Right, there is no closing bell on the blockchain. Crypto trades 24 hours a day, 7 days a week, 365 days a year.
So how can an AS model have a terminal time if time never technically ends in this market?
Yeah, how does that work?
This requires a brilliant adaptation by the algorithm designers. Instead of a hard closing bell, T becomes an artificial rolling time horizon. You might program the model with a constant 24-hour terminal time, or maybe an epoch based on funding rates.
So it's just a moving finish line?
A moving finish line that enforces discipline. Even though the market doesn't close, the algorithm is forced to behave as if it needs to flatten its inventory in the near future.
Oh, that's smart.
Yeah, the math dictates that as the time horizon shrinks toward that artificial T, the urgency to fix inventory imbalances increases exponentially. It prevents the bot from holding on to a bad position for weeks, hoping the market will turn around. It forces a timeline on the risk.
Okay, so we have current price, we have volatility, and we have this artificial urgency of terminal time. Now we get to the output. So what does this all mean for the actual price? How do these inputs generate the bid and ask?
Here we have to calculate the optimal spread. This is the distance between the ask price, delta A, and the bid price, delta B. And this spread is heavily controlled by a crucial user-defined variable called the risk parameter, represented by the Greek letter gamma.
Gamma. The source text explicitly states that the higher the risk parameter, the wider the spread. Let's unpack the personality of gamma, because I love this. If I program my bot with a very high gamma, I am basically creating a deeply paranoid, risk-averse machine.
Highly paranoid. Gamma essentially acts as a multiplier on the volatility sigma.
So if the market starts getting volatile, if sigma spikes and my gamma is high, my bot is going to demand a massive profit margin to justify staying in this terrifying market. Instead of a 2-cent spread, it might widen its quotes to a full dollar spread.
The high gamma bot says, I will only provide liquidity in this hurricane if you pay me an exorbitant premium for the danger I am putting myself in.
And conversely, a low gamma creates an aggressive, confident bot. It narrows the spread, ignoring the hurricane, jumping in to capture maximum volume, betting that its speed can outrun the danger.
Exactly. The optimal spread breathes in and out, constantly expanding and contracting based on the interplay between the real-time volatility and your pre-programmed gamma risk tolerance.
That dynamic spread is so elegant. But we still haven't solved the existential threat, right? The falling knife scenario where I accumulate way too much of a dying asset.
Yeah.
How does the Avellaneda-Stoikov model actually manage my bag?
We have arrived at the absolute crux of the model. The genius of Avellaneda and Stoikov was abandoning the idea that the public market price is the only thing that matters. They introduced the concept of the reservation price.
The text highlights this as the inventory term in the math, driven by the variable Q sub t, which is your current inventory position. Let's do a deep dive here. Walk me through the mechanism of how this subjective price is actually formed.
Imagine the public spot price of wETH is $3,000. A naive bot centers its bid and asks perfectly around 3,000. It bids at 2,995 and asks at 3,005. The public price is its anchor.
The AS model cuts that anchor.
The AS model says the public price is completely irrelevant if my internal inventory is unbalanced. It calculates an inventory term based on Q sub t. If your inventory is perfectly neutral-like, you have equal amounts of USD plus and wETH, your reservation price equals the public spot price.
Makes sense.
But the moment you take on inventory, your internal baseline shifts away from the public consensus.
Let's run a scenario with actual logic from the text. Let's say the market has been dipping and my algorithm has been dutifully buying wETH all morning. My Q sub t is now highly positive. I am heavy on wETH and dangerously low on USD plus cash. What happens to my quotes?
The math senses the heavy Q sub t. The output dictates that your internal reservation price must dynamically decrease below the public $3,000 spot price. Your new subjective baseline might become, say, 2,990.
So my entire spread shifts downward. The text specifies that the ask price decreases. Why?
Because you are desperate to offload your excess wETH to get back to a neutral state. By lowering your ask price, your wETH becomes the cheapest on the entire market.
Right, I'm undercutting everyone else. It's like the algorithm is throwing a fire sale to dump excess stock.
You are mathematically bribing the market to take the toxic inventory off your hands.
But the second part of the logic is where it gets really aggressive. The text says that while it decreases the ask price, it decreases the bid price even more.
Think about your internal state. You are already drowning in wETH. What is the absolute worst thing that could happen right now?
Someone's selling me more WE.
Precisely. If you leave your bid anywhere near the public market price, someone is going to hit it. So the model violently drops your bid price way, way down, maybe all the way down to 2,950.
So while I'm throwing a fire sale out back, I am simultaneously putting a massive not buying sign on the front door. I am making my bid so insultingly low that no rational human or algorithm would ever choose to sell to me.
You have effectively shut off the intake valve while opening the exhaust valve as wide as possible.
And if the situation reverses, say Q sub T goes negative, I've sold too much wETH and I'm practically out of stock.
The math just inverts. Your reservation price shifts violently upward, maybe to 3,010. You raise your ask to the moon, making your remaining wETH far too expensive for anyone to buy.
Right.
And you raise your bid above everyone else in the market, aggressively outbidding your competitors to vacuum up whatever wETH is available to replenish your reserves.
You hoard what little you have left while throwing a buying frenzy. The bot literally alters its perception of value based purely on its own survival instincts.
It's a mathematically perfect self-correcting feedback loop that almost guarantees you will constantly revert to a neutral inventory, protecting you from the falling knife.
Okay, wait, I have a massive structural pushback here.
Let's hear it.
This sounds brilliant in a vacuum, but markets aren't vacuums, right? They are highly adversarial. If I am running this bot and I aggressively lower my bid because my inventory is heavy, aren't I just broadcasting a massive signal to the rest of the market that I am desperate and weak?
You are absolutely telegraphing your internal state.
Then couldn't predatory algorithms or, MEV bots see my not buying sign, realize I'm trapped with heavy bags, and intentionally squeeze me? Like they could mathematically manipulate the price further down just to force my bot to panic sell at a massive loss to them.
That is an incredibly astute observation, and it brings us directly to the precipice of our next major topic. What you just described is exactly why the original Avellaneda-Stoikov model, which was built for the relatively controlled environments of Wall Street fiber optic networks, it completely shatters when you drag it onto a public blockchain.
Now, the blockchain reality check.
Yeah. When you take this pristine mathematical theory into the decentralized finance space, the friction of the real world introduces variables that Avellaneda and Stoikov never had to account for back in 2008.
Right.
The source text outlines 3 specific, brutal challenges.
Let's tackle challenge number 1, which is network latency. In traditional high-frequency trading, firms spend billions of dollars physically digging trenches through mountains to lay fiber optic cables in a straight line from Chicago to New York just to shave 3 milliseconds off their transaction time.
Because speed is alpha. On Wall Street, if your AS model updates your reservation price, that new quote is live on the order book almost instantaneously.
But on Ethereum, we don't have milliseconds, we have block times.
Currently, an Ethereum block is validated roughly every 12 seconds.
12 seconds in algorithmic trading isn't just an eternity, it is a geological era. Walk me through what actually happens during those 12 seconds. Like, I submit my beautifully calculated order, and then what?
Your transaction doesn't go straight to the market, it goes into the mempool.
The waiting room of the blockchain.
Exactly. It sits in a massive public pool of pending transactions, waiting for a validator to pick it up and include it in the next block. And while your transaction is sitting there exposed in the waiting room, the rest of the market is still moving.
So, my bot looks at the spot price of 3,000, runs the AS math, and submits a quote. But by the time the 12 seconds pass and the validator actually executes my trade, the global price of wETH might have suddenly crashed to 2,900.
And your bid, which you thought was cleverly placed at 2,995, is now massively overpriced.
Oh man, I just bought an asset for $95 more than it's currently worth. I got picked off.
You didn't just get picked off, you got hunted. The mempool is often referred to as a dark forest. It is crawling with predatory bots, searchers who do nothing but scan the waiting room for outdated quotes.
Right.
They saw the market drop, they saw your 2,995 bid still sitting in the mempool waiting to be processed, and they instantly bought wETH elsewhere for $2,900 and slammed it into your bid for a risk-free $95 profit. This is called MEV, Maximal Extractable Value.
That is utterly terrifying. How does our blueprint solve this? How do you mathematically protect a quote that has to sit in a dark forest for 12 seconds?
The source text introduces a profound statistical defense mechanism. It's called the random walk model.
A random walk. I've heard this term in physics and statistics, usually involving drunk people staggering around. How does it apply to our latency problem?
The drinker's walk is the classic analogy. Imagine a person standing under a street lamp. They take a step every second, but the direction of each step is entirely random. Forward, backward, left, right.
So after 12 seconds, I have absolutely no idea exactly where they are standing.
True. But mathematically, if you know the length of their stride, you can calculate the statistical radius of how far they could have possibly wandered from the street lamp in those 12 seconds. The algorithm applies this exact concept to the price of wETH.
Okay, let's tie this back to our variables.
The length of the stride is determined by our old friend volatility, sigma. If volatility is low, the price takes tiny steps. If volatility is high, the price takes massive, violent strides.
So the algorithm looks at the 12-second latency delay. It looks at the current volatility, and it calculates a probability radius. It basically says the price is 3,000 right now, but based on how violent the market is, in the 12 seconds it takes for my order to actually go live, this price could randomly walk anywhere between 2,980 and 3,020.
Exactly. The algorithm maps out the blast radius of the unknown future.
And what did it do with that radius?
It defensively widens its spread to absorb the absolute worst-case scenario. It says, I cannot trust the 3,000 spot price, so I will price my quotes as if the asset is already at the very edge of that random walk. It mathematically pads its margins to survive the delay.
That is a brilliant defense against time itself. But it comes at a cost, right?
Yeah.
Because if you are constantly widening your spread to hide from latency, your quotes become less competitive. You might protect yourself from getting picked off, but you also might price yourself out of getting any normal trades at all.
Welcome to the brutal reality of market making. It is a constant, agonizing compromise between safety and profitability.
Which leads perfectly into challenge 2 from the text. The cost of doing business. Gas.
Ah, gas fees. The silent executioner of mathematically perfect algorithms.
In DeFi, the blockchain isn't a free public utility. Every single computational action you take, placing an order, canceling an order, shifting your reservation price, requires you to pay a network fee to the validators for doing the work.
Right. And on Wall Street, transaction fees are microscopic, often a tiny fixed fraction of a cent. You can place and cancel 10,000 orders a second and barely feel the cost. But on-chain, gas fees are dynamic. They are based on block space supply and demand.
I mean, I've seen Ethereum gas fees spike from 50 cents a transaction to $100 a transaction in the span of 3 minutes during a volatile market event.
Now put yourself inside the AS algorithm. You calculate a perfect spread. You capture a trade that nets you a beautiful $2 profit, perfectly balancing your inventory.
A triumphant victory for the math.
Except the network charged you $5 in gas to execute the trade.
So I just successfully executed a mathematically perfect trade that left me $3 poor.
Yep.
But wait, if my bot is constantly adjusting its quotes every block to react to the random walk in its inventory, won't it just bleed its entire capital reserve dry through gas fees alone?
It will bankrupt itself in an hour. This is a massive flaw in porting traditional models on-chain. The AS model assumes frictionless updates.
So how must the math adapt?
The blueprint highlights that gas costs must be introduced as a fundamental negative parameter before any trade is approved. The algorithm cannot just look at the spread profit. It has to calculate the expected value of the trade minus the real-time base fee and priority fee of the network.
It basically has to ask, is the spread wide enough to manage my inventory risk, completely cover the dynamic gas fee, and still leave me with a net positive fraction of a cent?
Yes. And if the answer is no, the algorithm must simply sit on its hands and refuse to update its quotes, even if its inventory is dangerously unbalanced. It has to tolerate a certain amount of inventory risk simply because the cost of fixing it is too high.
Wow, it's a game of chicken with the network fees. Fascinating.
Oh.
Okay, let's hit the third challenge. The text brings up AMM and PMM mechanics.
Automated market makers and proactive market makers.
I am going to admit complete structural ignorance here. The source mentions that we have to translate our model from order book logic into liquidity pool logic. I know that traditional exchanges use an order book, a literal list of bids and asks, but DeFi mostly uses AMMs governed by a mathematical curve, usually expressed as x times y equals k. Break this down for me. How does a simple algebra equation replace a human order book?
It is arguably one of the most important inventions in modern finance. Let's build a pool. Instead of a list of buyers and sellers, an AMM is a smart contract that holds a big pile of two different tokens, let's say apples and oranges.
Okay, I have a big glass bowl on a table. I put 100 apples in it and 100 oranges in it.
The x is the number of apples. The y is the number of oranges. The formula says that x multiplied by y must always equal a constant number, k.
So 100 apples times 100 oranges equals a constant k of 10,000.
Exactly. That 10,000 is carved into stone. It can never change. Now, a trader comes along. They want to buy some of your apples. To take apples out of the pool, they must put oranges into the pool in such a way that the total product still equals 10,000.
Okay, let's say they want to buy 50 apples. They take 50 apples out. The pool now only has 50 apples, which is our x. To keep the constant k at 10,000, the pool must now hold 200 oranges. So the trader has to deposit 100 oranges just to get those 50 apples.
You just executed a trade without a human market maker. The mathematical curve dictated the exchange rate. But here is the critical part. Notice what happened to the price.
The first apples were cheap, but as the apples became scarce in the pool, they got exponentially more expensive relative to oranges.
This creates a continuous price curve. It guarantees the pool can always provide a quote, no matter how extreme the imbalance.
That's brilliant for the network, but how does our Avellaneda-Stoikov model actually interact with this? Because the AS model was designed to place discrete bids and asks on a linear order book.
That is the translation challenge, the text references. Advanced DeFi protocols like Uniswap v3 allow for something called concentrated liquidity. You don't have to spread your capital across the entire curve from 0 to infinity. You can choose to provide liquidity only within a specific, tight price range.
Oh, so you can recreate an order book bid and ask by deploying your capital into specific ticks on the AMM curve?
Exactly the mechanism. The algorithm has to take its optimal spread and reservation price from the AS math and run it through a translation layer that figures out exactly how to deploy the capital into the specific ticks of the AMM smart contract to simulate the intended quote, while factoring in the unique slippage dynamics of that specific pool.
Okay, let's take a deep breath and look at the absolute monster we have just engineered.
It is staggering.
We have an algorithm that has to track the real-time spot price. It has to calculate a rolling volatility standard deviation. It has to artificially induce panic based on a shrinking terminal time window.
Yeah.
It must constantly alter its subjective reality to find a reservation price that aggressively dumps heavy inventory.
Yes.
Then, it has to calculate the blast radius of a random walk to survive a 12-second journey through the dark forest of the mempool. It has to subtract violently fluctuating gas fees to ensure it doesn't bankrupt itself updating quotes. And finally, it has to mathematically translate all of this data into concentrated liquidity ticks on an AMM curve.
It is a multi-dimensional matrix of chaos.
And here is where I see the breaking point. You cannot manage that chaos with a static script. You can't just write a series of simple if-then statements. Like, if volatility is X and gas is Y, do Z, the permutations are infinite. The environment is actively adversarial.
A hard-coded script would break in 5 minutes during a major market event.
Right. You don't need a script. You need a brain.
Yeah.
You need a system that doesn't just follow rules, but actually learns from its environment and invents its own survival strategies.
Which brings us to the most exciting part of the blueprint. Part 4, the integration of the AI brain. The text introduces a reinforcement learning architecture known as PPO.
Here's where it gets really interesting. PPO stands for Proximal Policy Optimization. It is a highly advanced neural network framework heavily used in modern AI. Why proximal?
Proximal means it restricts how drastically the AI can change its behavior in a single learning step. In older AI models, if the bot discovered a strategy that worked well once, it might completely rewrite its entire brain to only do that strategy, essentially overfitting and destroying its ability to handle anything else.
Oh, I see.
PPO forces the AI to take small, steady evolutionary steps. It keeps the learning process stable.
To understand how we use this AI, we have to look at how we build its universe. The source outlines two critical vectors that form the interface between the AI and the market: the state vector and the action vector. Let's break those down. First, the state?
The state vector is what the AI sees. It is the dashboard of instruments reading out the reality of the market at any given millisecond.
The text specifically lists the inputs. The AI is fed the current price, its current inventory imbalance, the rolling market volatility, the real-time network latency, and the depth of the AMM liquidity pool.
That is the entirety of its existence. It does not know what Ethereum is. It doesn't read the news. It just sees this stream of 5 numbers constantly flickering and changing.
Okay, so it observes the state. Then we have the action vector. This is what the AI is allowed to do to interact with its universe.
The controls on the dashboard, based on the state it just observed, the AI outputs an action. According to the blueprint, it can adjust 2 things. It can set the spreads, meaning it decides the exact gap between the bid and ask, and it determines the size, which is how much of its total capital it wants to risk on that specific quote.
So it looks at the chaos, and it pulls the levers.
Yeah.
But this is the fundamental question of AI. How does it know which levers to pull? It doesn't have human intuition. We don't program a manual.
We give it an environment, and we define its purpose through a reward function.
The carrot and the stick.
What's fascinating here is how we train it. Reinforcement learning is often compared to a rat in a maze looking for cheese, but I prefer a different analogy. Imagine dropping a blindfolded person into a room filled with heavy wooden furniture. Their goal is to navigate the room.
They can't see the furniture.
Right. Every time they take a step and smash their shin into a coffee table, they feel pain. That is a negative reward. Every time they take a step and find a $100 bill on the floor, they feel joy. That is a positive reward. Through trial and error bumping into things, finding money, their brain maps the room. Over millions of iterations, they learn to sprint across the room flawlessly, maximizing the money and avoiding the pain, without ever actually taking the blindfold off.
We are training a neural network through mathematical pain and pleasure. We had to look incredibly closely at this reward function, because whatever equation we put into this formula literally dictates the soul of the machine. It defines what the AI considers good and evil.
And our source text explicitly defines this function. It is a beautifully concise equation. Profit term minus inventory risk minus gas cost.
This equation captures the entire existential struggle of the vendor's dilemma. Let's dissect the 3 components. First, the carrot, the profit term.
This parameter is pure, unadulterated greed. The AI receives a mathematical influx of joy for every successful trade that captures the spread. The more unrealized or realized profit it generates, the higher its score.
If this was the only thing in the formula, the AI would just turn into a hyper-aggressive, degenerate gambler. It would, quote, microscopic spreads, trade millions of times a second, and take massive unhedged risks just to hunt for every single fraction of a penny of profit.
It would chase the $100 bills while running full speed into the coffee tables. So we introduced the first stick, minus inventory risk.
The fear parameter.
We are actively punishing the AI for holding too much of one asset. If it gets greedy and accumulates a massive bag of wETH because it thinks it can make a quick flip, this penalty activates. The larger the imbalance in its inventory, the more severe the mathematical pain it feels.
I love this because we aren't explicitly teaching it the Avellaneda-Stoikov reservation price math.
Right.
We were just inflicting pain when it holds bags.
Exactly. And through millions of simulated training episodes, the neural network naturally discovers the principles of the AS model all on its own. It figures out, oh, when my bag gets heavy, the pain increases. If I lower my ask and drastically lower my bid, the market takes my inventory away, the pain stops, and I can go back to collecting profit.
That's incredible.
It independently invents the concept of a reservation price just to survive the reward function.
We are forcing it to balance greed against safety. It desperately wants the profit term, but it is terrified of the inventory risk penalty.
But there is a loophole here.
I see it. If I'm the AI and I want to avoid the inventory risk pain entirely, I could just rebalance my portfolio back to perfect zero every single time I make a trade. Like, I could place 1,000 tiny trades a minute to guarantee I never hold a bag.
You would achieve perfect inventory management.
But in the real world, on the blockchain, placing 1,000 trades a minute would incur hundreds of thousands of dollars in network fees. I would manage my inventory perfectly, but I would bankrupt the fund in an hour paying validators.
Which is why the third component of the equation is so vital, minus gas cost.
The reality check.
Yeah.
We induce mathematical pain every time the AI burns network fees.
By subtracting gas cost from the reward, you force the AI to be ruthless with its efficiency. It learns that it cannot afford to be hyperactive. It learns to tolerate a small amount of inventory pain simply because the gas penalty for fixing it is too high.
It learns patience. It waits for moments where the potential profit from the spread is large enough to cover the gas fee and outweigh the temporary inventory risk.
The AI is trapped in a multidimensional box. It must continuously maximize its expected reward by navigating the greed of the spread, the terror of the falling knife, and the frictional tax of the Ethereum network.
And because it's a deep neural network, it can find emergent strategies that a human quantitative analyst could never even conceptualize. Like, it might figure out that when latency spikes to 15 seconds and volatility drops, the optimal move isn't to change the spread, but to artificially skew the AMM ticks to capture a specific block builder's behavior.
Exactly.
It discovers these dark forest survival tactics through pure, relentless trial and error.
It is breathtaking to observe, but as our blueprint points out in Part 5, observing this in a training environment is profoundly different from unleashing it on the mainnet.
Right, a simulation is just a sterile laboratory. Step 7 of our source text warns that to make this actually work, you have to cross the chasm from the sandbox to the live battlefield.
The source outlines the mandatory upgrades required for real-world deployment. The first is infrastructural, connecting real APIs.
You have to unplug the AI from the mocked-up training data and plug its sensory inputs directly into the live veins of the market. The text mentions integrating with the Binance API for global price discovery and connecting to dedicated live Ethereum nodes for on-chain execution.
The AI must feel the true latency of the node. It must experience the sudden, unpredictable gas spikes of a real network congestion event. The training wheels come off.
The second upgrade suggested by the text is highly technical, but totally crucial. Upgrading the volatility models. It suggests that simply looking at a historical rolling window of volatility isn't enough. We need to upgrade to advanced mathematical models, specifically mentioning JACH-ARCH.
JACH-RCH. Generalized autoregressive conditional heteroskedasticity.
That is a phenomenal collection of syllables. Let's translate that into English. What does heteroskedasticity mean for our AI?
Without spiraling into a statistics lecture, JACH-RCH is a model designed to capture a very specific phenomenon in financial markets. Volatility clustering.
Volatility clustering. Explain that.
Markets do not experience randomness evenly. Calm periods tend to breed more calm periods. People get complacent. But when panic hits, like the COVID crash in 2020 or the collapse of the FTX exchange, volatility violently clusters together.
Right, it's just chaos.
Chaotic days are almost always followed by more chaotic days as liquidations cascade and panic spreads.
So a basic volatility model just looks backwards and says, wow, it was really volatile yesterday.
Right. But a Jurasat model analyzes the variance of the errors. It recognizes the clustering effect. It can predict that because we are entering a chaotic cluster, the variance of tomorrow's volatility will likely be extremely high.
So by feeding a JARSAID forecast into the AI state vector, we aren't just telling the blindfolded person what they bumped into yesterday. We are giving them an acoustic radar mapping the furniture they're about to hit tomorrow.
A perfect analogy. Forecasting volatility is the holy grail for an options trader or a market maker. If the AI senses an incoming volatility cluster before the spot price actually breaks down, it can preemptively widen its optimal spread, shift its gamma, and aggressively dump its inventory before the falling knife actually drops.
It essentially learns to predict the weather. The text also touches on expanding the strategy beyond just USD plus wETH. Scaling up to a multi-asset strategy, feeding dozens of pairs into the PPO's state vector simultaneously.
This is where the machine truly transcends human capability. A human trader sitting at a desk can intensely monitor perhaps 2, maybe 3 highly volatile crypto pairs at once.
Yeah, if I'm trading wETH, my eyes are glued to that one chart. I am blind to everything else.
A PPO neural network can monitor USD plus wETH, USD plus cbbtc, Solana, Chainlink, and 50 other assets simultaneously, updating its entire worldview every 12 seconds. And the profound part is how it manages the AS inventory risk across the entire portfolio.
Wait, what do you mean?
It might realize that wETH and cbbtc are highly correlated. They tend to move up and down together. So if it is holding a dangerous, heavy bag of wETH, but it simultaneously has a massive short position in cbbtc, meaning it owes cbbtc, it doesn't have, the AI might mathematically realize that the two risks cancel each other out.
Oh, wow. It realizes the wETH bag is actually acting as a perfect hedge for the Bitcoin deficit.
Exactly. So instead of aggressively dumping the wETH and taking a loss, it holds the inventory, saving the gas fees, because it understands the multidimensional risk profile of the entire 50-asset portfolio is perfectly neutral. It plays a game of multidimensional chess that a human mind simply cannot visualize.
That is awe-inspiring. But, and there's always a but, the author of our source text concludes with one final, overriding warning: the absolute golden rule of algorithmic trading.
Mathematical elegance is never enough. The text explicitly mandates that success requires relentless testing, constant monitoring, and continuous optimization.
You cannot just turn this AI on, walk away to the beach, and expect the money printer to run forever.
Because the market is not a static puzzle to be solved. It is a brutal, hyper-competitive, evolutionary simulator.
Yeah, if you built a clever AI that perfectly manages its spread in gas, someone else in a proprietary trading firm in Chicago is building a cleverer AI specifically designed to exploit the microscopic blind spots in yours.
Exactly. If your PPO algorithm develops a slight unseen bias, perhaps it tends to widen its spread a fraction of a second too late during a specific type of GRCH volatility cluster. A predatory MEV bot will eventually find that bias, and once they find it, they will relentlessly exploit it, slowly bleeding your liquidity pool dry.
You have to constantly retrain your models, stress test your assumptions against live adversarial data, and ruthlessly monitor your real-world performance against your simulated expectations. The war never ends.
It just gets faster.
We have covered an immense amount of ground today. We started with a simple vendor at a physical market, terrified of buying too many rotting apples. We journeyed into the elegant, self-correcting mathematics of the Avellaneda-Stoikov model, seeing how the subjective reservation price manipulates the spread to mathematically force the market to fix our inventory risk.
We tackled the severe structural realities of the blockchain, the random walk required to survive the latency of the mempool, the brutal tax of dynamic gas fees, and the translation of order books into the X times Y equals K curves of automated market makers.
And we saw how a proximal policy optimization AI, a neural network trained through the pain and pleasure of a carefully constructed reward function, can synthesize all of this chaotic data to dynamically navigate the dark forest.
It represents a remarkable convergence of human disciplines. You have the quantitative finance of traditional Wall Street, the cryptography and distributed systems of the blockchain, and the cutting-edge behavioral architecture of artificial intelligence, all fusing together into a single autonomous entity.
Which brings me to a final thought I want to leave you, the listener, with today. We talked about how these systems scale. We talked about the multi-asset strategies, the AI managing hundreds of pairs simultaneously.
The logical, inevitable endpoint of this technology.
Right. Think about the trajectory of that endpoint. If reinforcement learning agents like this PPO bot become the absolute standard across the entire global decentralized finance ecosystem, if every single liquidity pool, every trade, every bid and ask is managed by an AI that perfectly predicts volatility with jar siege, flawlessly prices in latency, and perfectly balances inventory risk against a rolling terminal time window,
you've eventually removed the human element entirely.
that's the question. Do we eventually reach a purely machine-driven financial system? A market where human emotions, the panic selling at the bottom, the euphoric, greedy buying at the top, are entirely priced out, where algorithms simply view human fear and greed as temporary mathematical inefficiencies to be mercilessly arbitraged away.
And if you remove emotion, what are you left with? Does it become a perfectly stable, frictionless utopia of infinite liquidity? Or does locking millions of AI bots in a closed-loop evolutionary war create entirely new, unimaginable types of systemic, algorithmic risk that no human could ever foresee?
A question for another day, and perhaps another era. But when you look closely at the architectural blueprint we've unpacked today, that fully autonomous future doesn't seem like science fiction anymore. It just looks like the very next step in the code.
The war continues.
Thank you so much for joining us on this deep dive into the architecture of algorithmic liquidity. Keep questioning the systems, keep exploring the hidden structures of the math, and we'll see you next time as we continue to map out the depths of the modern world.